Hello, people. Hopefully, you took a deep breath, cleared your mind here, and we're back to example number two. In this example, we are being asked to find a third degree polynomial approximation for e to the x at x equals 1. This time, they didn't give me the polynomial, so I have to build it myself. It's going to be centered at 0. And then we're going to use Taylor's inequality to find the range of possible values for e to the x at x equals 1 centered at 0. Okay, so two parts. First part, find a third degree polynomial approximation for e to the x at x equals 1 centered at 0. Okay, so what do we need to do? We need to take some derivatives. So f is e to the x. I'm going to go to the third derivative. So f prime is e to the x. That's easy. F double prime is e to the x. F triple prime is e to the x. And I stop. Now we're going to find f at the center value. The center value is 0. So this is f of 0 is 1, and f prime of 0 is 1, and f double prime of 0 is 1, and f triple prime of 0 is 1. Oh, well, that's easy. So therefore, my polynomial third degree of x follows the pattern f of 0 plus f prime of 0 times x minus 0 plus f double prime of 0 over 2 factorial times x minus 0 squared plus, and I'm going to put this one on the other side over here, f triple prime of 0 over 3 factorial times x minus 0 to the third. This is the setup we need, but because we know these values, I know it's 1 plus 1 times x minus 0. Oh, x minus 0 is just x, so this is just x plus 1 over 2 factorial times x minus 0, which is, x squared, plus 1 over 3 factorial times x to the third. Hey, would it be okay if I rewrote this as x squared over 2 factorial? That would make it look a little bit nicer. And if I rewrote this as x to the third over 3 factorial, haha. This is the third degree polynomial approximation for e to the x at x equals 1, centered at 0. But we want to find the approximation for x equals 1. So we're going to say e to the 1 is about p sub 3 of 1, which means we're going to substitute a 1 wherever we see, by the way, that's 2, an x. And by the way, that's 6. So if I did this correctly, let's see, 1 plus 1, that's 2, plus 1 half plus 1 sixth. I think that's right. And then these two together, I need a common denominator, which I think is 6. So I need to multiply this by 3, that's 3, so that's 3 plus 1, that's 4 sixths, which is 2/3. So this is 2 and 2/3, or 8/3. This is my approximation. Happy. Now, use Taylor's inequality to find the range of possible values for e to the x at x equals 1 centered at 0. Well, what do I need to do? If I go back, it says use Taylor's inequality. Okay, so here's Taylor's inequality. Now, remember, when we came over here, we said that this has to equal the remainder, or the error is the difference in the actual value minus my approximation. So let's start there. So e to the 1 minus, can I just write e? Does that make it, yeah, e to the 1 is just e. E minus my approximation has to be has to equal this, right? What was the x value that I substituted? 1. And this has to be less than or equal to the whole max of the blah 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 over blah 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 times blah blah blah. Okay, so let's fill in the blah blah blahs. We know that we went to the third degree polynomial, so we're going to say this is 4 factorial, and this is going to be to the fourth power, and we're going to find the fourth um, derivative. But we're going to have to evaluate it at that z value. We're going to come back to this here in a little bit. My x value, which was 1, minus my center, which was 0. Oh, so this is really just going to go away. 1 minus 1, 1 minus 0 is 1 to the fourth power. So this goes away. It becomes 1, and so I'm left with this. So here's what I know. I know that the difference is less than or equal to this. Well, what was the fourth derivative of the function? Well, we didn't find it, but the fourth derivative would be e to the x. Well, what's the maximum value of e to the x? Oh, wait. Remember, this z value should be between my center and my x value. Well, if I'm taking the derivative of if I'm taking the fourth derivative, which is e to the x, that means the lowest value here is e to the 0, and the highest value is e to the 1. But I can't use e to the 1 because that's part of what I'm looking for, right? Like I'm trying to approximate e to the 1. So that's kind of weird. Remember, e to the 1 is about 2.718. So why don't I just say it definitely has to be less than 3, right? Because if this is the actual maximum, well, why don't I just make it easy on myself and say, well, look, I know that it's supposed to be this value, but this value is definitely less than or equal to 3. So why don't I just say 3 to make it nice for everybody? By the way, once I finish this, if I reduce this, remember 4 factorial is really 24. And if I reduce this, that's 1/8. So what we're saying is that because I used this approximation and I calculated this as my upper bound for the error, that we can calculate what values E could be between according to my approximation. So here's what we go to. Remember, to solve inequalities, we have to create kind of a single inequality here. Something like this. And then we're going to add 8/3 on both sides. So we're going to add 8/3 here. We're going to add 8/3 here. Or I guess on all 3 sides, we're going to add 8/3 here because this is going to leave us with E. And then on this side, we're going to find common denominators. Okay, so common denominator would be 24. So if I multiply this by 3, that's going to be 3 on top. Numerator, multiply this by 8, that's going to be 64 on top. So 64 plus 3, that's 67. So 67 24ths. If I do it over here, now I have to subtract, but I think the common denominator is 24 also. So if I multiply this by 8, I'm going to get 64 positive. Multiply this by 3, that's going to give me negative 3. So 64, that's 61 24ths. So according to our approximation, the range of possible values for e to the x at x equals 1 centered at 0 is this range of values. How did I know that? Because I found my approximation, because I estimated my remainder and really created a bound, an upper bound that my remainder has to be less than. And in doing so, using the idea that actual value minus, or the exact value minus my approximation has to be equal to the remainder, which is less than this number, I'm able to get a range of values that e to the x could be, and it is. Right? So let's double check that. You and I both know that you can find E on the calculator here. So this is the actual value. We're saying that this number has to be between 61/24 and 60, was it 67? Yep, 67/24. Oh, not 677, 67. And it is. So this was my range. So the actual answer, which is this, had to be between, I was predicting was going to be between these two things according to my approximation, and it is. Now, what does that mean? If my approximation had only used two terms, or I'm sorry, gone to the three terms and gone to the second degree polynomial, that means my range would probably be a little bit bigger, right? It'd be a little bit wider. So the more terms, the better the approximation. The better the approximation, this range kind of closes in and it gets tighter around the actual value that we're looking for. I'm going to go ahead and ask you to take a deep breath and let your mind rest. I know this is really, really theoretical, and a lot of I don't know, there's a lot of pieces to this, but fundamentally, I need you to just go back and remember this idea from here, that we're finding the leftover. And because it's hard to find the leftover, we're approximating the leftover and saying this remainder cannot be bigger than a certain number. And the reason we're looking for that is because if you were to add it to the approximate value, then that would give you the exact value. Or, said another way, what we're really finding is the error in my approximation in finding the exact value.